Okay, so today we're going to be doing another 2D kinematics problem, and we'll get right into it. So an arrow has a launch speed of 18 meters per second and is fired at an angle of 35 degrees above the horizontal. If it is to hit a target 25 meters away, at what height should the target be placed? Okay, so let's just read through the problem again and find any key information. So the first thing we notice is that we are given the launch speed, in other words, the initial velocity. We're given the angle at which the arrow is fired, so this is a vector with an x and y component above the horizontal. If it is to hit a target 25 meters away, at what height should the target be placed? So let's imagine like this arrow being shot, and let's say it hits the target spot on. The height of that target is what we're trying to determine. So in other words, we're also trying to determine the ending height of the arrow. So at what height will the arrow, or what height will the arrow end at? That's essentially another way to think of this question. So using the information that we're given, well, first let's draw a diagram. Sorry, I'm getting I'm getting ahead of myself, but it's always helpful to start with a diagram. So this is the horizontal, okay? And this is the arrow being shot 35 degrees above the horizontal. So that's 35 degrees. And this would be the arrow, at least the velocity of the arrow. And this is 18 meters per second, okay? And it'll keep going until it reaches a point right here. Let me erase this section because, oh, we don't need this. Okay, there we go. Right here, this is 25 meters. Okay, and this is the ending height of the arrow, also known as the height of the target. And we'll just call this delta y. Okay, y final minus y initial. Okay, so we'll just plot out well, not plot out, but we'll put down our variables: x naught, x final, v naught in the x direction, v final in the x direction, acceleration in the x direction, and time. Okay. So let's just fill these out. The initial position along the x-axis, we're just going to say is 0, okay? And it travels 25 meters. So already what we're saying here is that from this half to this half is movement in the positive direction, okay? Meaning all of the other variables have to follow true to that. So the initial velocity in the x direction is, sorry, it's not 18 meters per second. We're given a vector that we have to find. We have to find the x and y components of this vector to find specifically what is its velocity in the x direction and solely the x direction, and what is its velocity in the y direction and solely the y direction. So in this case, we're just going to solve for the velocity in the x direction. Okay, so this is 35 degrees right here. What we can do then is use a bit of trig using, let's see, well, we want this length, so we want cosine. So cosine 35 degrees is equal to x over the hypotenuse, so we're just going to say we'll just say vx over 18 meters per second, obviously. And then if we multiply both sides by 18, we get 18 cosine 35 is equal to vx. And the velocity in the x direction is, after a few computations, we get 14.74 meters per second. Okay, so what we can do then is plug that in for this variable. Okay, and since the velocity does not change in the x direction, we can also plug that in here because we're assuming air resistance is negligible, okay, which means the acceleration in the x direction is 0, and the time we do not currently know. Okay, so those are the values for some of the x variables, and now we have to do the same for the y. Okay, so y naught, y final, initial velocity in the y direction, and final velocity in the y direction, acceleration in the y direction, and time. Okay, so let's just say y naught is 0, and we have to establish which side is positive and which side is negative. So if y naught is right here, okay, it's along the horizontal, and this right here is y final, and delta y has to be a positive value, then from here to here, trending towards this direction, is the positive side. Okay, so all of our variables have to correspond to that. So the initial velocity in the y direction, once again we have to use a bit of trig right here. This time we're going to use sine. 35 is equal to Vy over 18. Multiply both sides by 18. It's the same math over here. Okay, I won't skip it. I won't skip it in case it's... I'll show my work. 18 sine 35 is equal to Vy. Okay, and then run the computation in the calculator, and Vy is equal to 10.32 meters per second. Okay, and what we can do then is plug that in here. Now, we can't necessarily plug it right into V final because velocity in the y direction is changing, okay? In fact, we don't know what the final velocity is in the y direction because it's launched, it starts to fall, but we don't know what its velocity is when it hits the target, at least in the y direction. Well, yeah, at least in the y direction. So we don't know that value. Acceleration in the y direction, though. So once the arrow is shot, it starts to trend towards this direction. Oop, can't use that color. Let me change this color right here. One sec. Okay. It starts to trend towards this direction. So the arrow is initially moving upwards, but ultimately its movement is trending downward. And I like to think of acceleration that way, as sort of like the trend, the direction that the object is moving towards. And in this case, it's moving towards the negative half because we established that this upper half is positive. So the acceleration in the y direction is negative 9.8 meters per second squared. We don't know time, but we will find that out. Okay, so now let me clear up a little bit of space. Alright, so now let's get into using our kinematic equations. So over here we have 3 unknowns. This looks like a lot of unknowns. If you don't know where to go, it's usually a good idea to see which side has more unknowns, which side has less unknowns, and then to go with the side where you know more. So we're going to start with the x half. This is not always a hard and fast rule, but it's something that you can use to intuit problems. You could also just mentally check, okay, do I have only one unknown when I plug my known values into the kinematic equations? And if you can't find an equation where there's only one unknown, then it must be the other half, or you must have forgotten something. So let's just start with the x half, and the equation that we can use is, let's not use squares. the equation that we can use is x is equal to x naught plus v naught t plus, oh, that t is terrible. Let me try and make that a little longer. There we go. This plus sign is also really bad. Let me redo that. Okay, t plus 1/2 a t squared. Okay? So we know that x final is 25, so we can put that right there. We can plug in 0 for x naught. I'm just not even going to bother writing that in. We have v naught in the x direction, which is 14.74. Okay, and then time is an unknown. And over here in this term, acceleration is 0, which makes this entire term 0. So I'm not going to add that. I mean, I just did, but you could see why I wouldn't have to add it into the rest of the, oh dear, into the rest of the equation. There we go. Okay. And now we're left with an equation with just one unknown, just t. So we can divide both sides by 14.74 and get that t is equal to 1.696 seconds. Okay, that's great, because now we can use this time to replace the unknown in the x half, 696, and in the y half, 696. Okay. Ultimately, we want to find y final, because that's going to help us compute delta y. And now that we have t, we can actually use a kinematic equation in the y half, and that equation is in fact the exact same as the one we used for the x half. So let me just clear up some more space because this might take a bit of room. Okay, so it's going to be, let me write it over here, y is equal to y naught plus v naught t plus 1/2 a t squared. Okay, so this is what we're trying to find. So it's actually pretty convenient that the equation itself solves for what we're looking for. But anyway, y is equal to, let me fix that y is equal to, y naught is 0, so I'm not even going to bother plugging that in. V naught in the y direction is 10.32 meters per second, obviously. Time is 1.696 seconds plus 1/2 acceleration, which is negative 9.8 meters per second squared, and time is 1.696 squared. Make sure not to forget to square, and make sure not to forget that there is a 1/2. I didn't write units, but I highly recommend that you write units. Whenever I'm doing it on pen and paper, I write units. It's just this is on the computer and I'm using a mouse, so it's not necessarily super friendly to write every single little detail, especially since the paintbrush is so thick. But anyway, plug these values into a calculator, compute, and you should get 3.419 meters. Before we box this off, let's look back at the question and consider sig figs. So our sig figs should be, we should have two sig figs. This is going to be 3.4 meters. And that is the height that the arrow will end. That is also the height the target should be so that the arrow hits it. Alright, thanks for watching. Might be another upload later today. If not, sometime later tomorrow maybe. But we'll just see. Anyway, thanks for watching.